This one for all my peeps that pass. God bless they rest. And check it out. Now I'm pound cause it's mad real.
Yo, it's time for Carnegie Mellon University's Future Data System Seminar Series. This seminar is made possible by Google.
Hi guys, let's get started. Super excited today to have Vinoth Chandar. He is the creator of Apache Hudi, which I'll talk about today. He's also the co-founder or founder of OneHouse, the sort of commercial backing, expanding and building and commercializing Apache Hudi. So we're super excited, happy for him to be here with us today for our seminar series. Again, as always, if you have questions for Vinoth as he gives the talk, please unmute yourself and ask a question anytime, and that way he's not talking to himself for an hour. And Vinoth, thank you so much for being here. Thank you so much for being here. The floor is yours. Go for it.
All right. Thanks so much for being here. Hello, everyone. I'm very excited to be here speaking to you all about the Apache Hudi project. Like many of you, I was a grad student myself, roughly 17 years ago, though, at UT Austin. So yeah, I've been preparing for the talk, putting the slides together over the weekend. Definitely reminded me of my own assignments and projects. So thanks for taking me back to those golden days. All right. Formally, my day job is running, hopefully now a somewhat kind of like well-recognized data startup, OneHouse in the data lakehouse space. Equally important to me is my OSS hat as PMC chair for the Hudi project, also a member of the Apache Xtable project that brings table format interoperability. And previously, I've been part of database and analytics data platform teams at Uber, Confluent, LinkedIn. Fortunately, during some hypergrowth phases of these companies, which helped me learn a lot about these kind of data distributed systems. All right. This talk is kind of 8 years in the making, starting with us open sourcing the Hudi project in early 2017 at Uber. And Hudi is the earliest data lakehouse tech. And it introduced a lot of the database on the lake ideas and architecture. And Hudi today powers some of the largest data lakehouses in the world, including, of course, Uber, Amazon, Walmart, a good chunk of Fortune 100 companies. That has given us also a lot of perspectives on real production challenges that people hit when they're running these workloads, which I hope to share with you today. So the goals for today, we want to first cover how this lakehouse architecture came to be and what are the motivations for doing something like this. Then we want to cover the core design trade-offs. We'll cover all the important problems being addressed in the space and leave you with some thoughts on what the future holds. Right. Our story takes us back to Uber in kind of like crazy growth mode. We're adding new features, a lot more users, all led to more and more data. We had, my previous job was at LinkedIn, like a company that was pretty well known for its data infrastructure back in the day and today as well. We had built a traditional file-based data lake. So if you're unfamiliar with the data lake, what this means is data lake is a very large collection of files stored on cloud storage like S3 or a distributed file system like HDFS. You then run jobs, which are basically processes that read, process, write new files. So you crunch files, produce new files using distributed frameworks like Spark or MapReduce. So this is generally how the thing runs. And at Uber, as you would imagine, trips was like a very core data set. We wanted to ingest trips in near real time into our data lake and write them out as Parquet files, which is like a columnar file format widely adopted by the entire industry to do analytical queries for data science, analytics, machine learning, what have you, right? And then, our kind of state-of-the-art file-based data lake ran into a lot of problems, right? So one was, correctness issues simply because we're just producing files. So if there was a partial write or a duplication in the data, anything like that, we had no way to query these tables consistently, right? We could see some like phantom writes and things like that. Two, they're slow and fragile because as you can see, there was 120 terabytes we are bulk ingesting every 8 hours. It's just kind of like nuts when the actual data change is only less than 500 GB. But like again, in the lake, you deal with files. You really don't have a good abstraction to kind of apply updates or things like that. And the other thing is it's too expensive, the whole thing, because it's not the only thing that we do. We also process the data. For example, a simplest job would be trips are happening, you would want to, and then let's say the trip records are in local currency or something. And then we just want to join it with a standard currency conversion table and say, okay, how much revenue did we book, right? So even all those things crunch similar amount of data. So because it was all like full recomputed every 8 hours, hours and hours of delay, right? And this wasn't like really scaling for us, right? And the reason was data lakes were pretty limited back then, right? At a high level, there was some fledgling, SQL data frame engines, which are reading and writing, crunching files. That's basically what we had. You mostly dealt with up and only files. You write files, you write more files, right? And there is essentially coarse partitioning, which is essentially splitting files into folders to kind of mimic, I would say, a poor man's index, if you will, to kind of do things more efficiently. There's no table or concurrency control. You have to manage all these files yourself, clean them, like put the right ones in, get the wrong ones out, things like that. And as I mentioned, you reprocess things over and over time, which means the writers are writing more, the readers are scanning too much, right? By the time I worked on a relational database and a key value database at my previous jobs, I'd come to appreciate kind of how databases simplify life, right? It's specifically of interest was the storage manager functionality here. In this talk, we kind of talk about it interchangeably as the storage engine. And if you look at it, it provides a much more efficient, a higher level abstraction to work with data, right? The core maintenance aspects were all standardized by database services, right? You don't deal with all of them. You write and read data, right, at a record level abstraction, right? If it helps kind of internalize MySQL, the DBM MS supports different storage engines with different trade-offs, right? For example, like DB is a B plus tree, and MyRox is like a RocksDB LSN tree, one optimized for reads, another optimized for writes. All of this is nicely packaged hidden under the SQL interface that you see on MySQL, right? But lakes, like we mentioned, work with files, right? Not records, right? So on the left, if you look at it, a simple job of transforming some data, there are some user events, there's some user profiles, and we're trying to do some aggregate stats, right? Typically, the way you did that was you scanned a bunch of files. You really didn't know what changed. So you scan heuristically last 7 days, right? In the hope that, only last 7 days files had folders had any updates or anything like that. Then you join them. You typically read the previous state of the table and you completely produce new sets of files and flip a pointer in the catalog or something to say, this is now the new table, right? This is kind of like how the whole thing worked. But record level operations are more the natural way, right? Like batching writes helps, obviously, right? When you're in this kind of thing, but rewriting full partitions is often not necessary, and it's often a lot of wasted work, right? Most of the times, only a small part of the data has actually changed since you last, computed a target table, right? So if we had record level operations, we could process data more efficiently, as you would see on the right. You would be able to query the records that changed, scan them, join them with another table, and then just update or merge them directly onto a target table, right? This is a more natural, more efficient way of dealing with this, right? And you can relate to probably how you build tables on a relational database, right? How you maintain your ETLs or something. So, but this is not how it worked, right? But data lakes are not entirely bad. They are the most scalable and the most cost-effective way to handle large amounts of data, even today, right? Say anything beyond like a 10 terabytes, something like you should put on something like this. That power comes from a few things. One, vast, inexpensive storage. I say infinite storage, I mean, obviously it's not theoretically infinite, but you get the point, right? You just like write data into S3 and you like they deal with it, right? So and then it's great for it can hold some data in motion and also data at rest, right? It's your one big repository where you can keep dumping as much as you want. The other really nice thing was you had a lot of these purpose-built scale-out distributed query engines, right? You had one for ETLs, you had one for data science workbenches, things like that. You have interactive query engines. All of them kind of operate in a sort of like a headless mode on top of this data. I say headless because typically ETL job is run on a schedule. You take a Spark, a Hive job or something like that, and every 6 hours, every 3 hours, 1 hour, it runs on a schedule, right? When it's not running, it's relinquishing all the compute, which makes the whole compute architecture efficient here, right? You could also have a long running thing. Like for example, many of them have a Presto or a Trino or some interactive engine that is just hooked up to your storage that people like analysts go on, right? Run your queries. This is like your data warehouse query use case, right? And you can also have data science workloads where, it can be anytime, right? Like it really depends on when the data scientists are working. They may spin up a cluster, do some analysis, shut down the cluster. So this whole thing was very efficient, the architecture, because you had lots of storage, very cheap, very scalable, combined with like multiple engines, which, come up and go, right? As on demand, right? So this was like a real good power for the architecture. So taking us all the way back to our Uber team, what we asked ourselves was, can we, what if data lakes can be more like databases? We can interact with it in a similar fashion without losing any of these benefits, right? We thought this would be a new adventure, in fact, a new model to actually retain all the strengths of the data lake, which is storage, compute, columnar files, just having everything be stored on the lake, and actually introduce this sort of like storage engine functionality, transaction indexes, updates, deletes, automated table maintenance, CEC, and all of that. Right. So in effect, we're adding like a layer in between the query engines and storage in the previous diagram that we saw. Right. So this is how we conceive Hudi. The right way to look at Hudi is like a storage engine, which is embedded into your SQL engine, right? And it has a table or a storage format designed to support its functionality, right? And we retain the headless architecture of the data lake, right? These engines can still like come up and go. This makes some design changes very interesting, as we'll see later. And the engine also performs fully distributed read writes against cloud storage, right? So if you add the thing that we considered back in the day was use a system like Kudu, for example, which was like a storage system that came up back in the day, which address some of these issues, right? But the thing is, if you add any storage server in front of a cloud, for cloud storage, that will invariably turn into a bottleneck. You don't want anything between your scale out distributed compute and your scale out cloud storage. So the third thing is, again, as I mentioned, this is embedded into the engine. So typically embedded engines are single process, right? If you look at like for my previous job at LinkedIn, we worked with LevelDB, RocksDB, BerkeleyDB, the embedded databases, but those typically sit within the process. Here, this is almost like a embedded database, which is distributed, that you put into an existing framework, like let's say Spark, right? So our idea here is, if you take an existing distributed framework like Spark, you embed something like Hudi, the combination makes this an embedded headless distributed database built purely on top of cloud storage, right? Which is a very exciting thing for us to kind of start building. And we believe that if we build this, it'll kind of like raise the bar, make us do more things on the lake. Right. That was the core motivation for us. Right. So with this, I think there are two major components to Hudi. One is the storage engine that we talked about, and the storage format, right? So in the next sections, we will cover the format and then go into how the engine's implemented using that. All right. So just to dive into this slide kind of gives you a schematic of the Hudi storage layout, right? On the left lower left corner, you have a Hudi table sitting on top of cloud storage, which now expands out into some directory storing data and some directory storing metadata, right? So the data directories are, the table can be partitioned or not partitioned, but partition is merely think of it as a folder within the table, right? That logically partitions. For example, the most common way to partition data on the lake is by date, right? You store event logs by the date in which the events are produced, things like that. Within each partition, we have what are called file groups. So file group is effectively the core, like a core abstraction or a concept inside Hudi, where records belonging to that partition are kind of mapped to a file group at any point in time, right? So it's essentially a distribution of records into different file groups. And each file group then has, like different versions of files. So it basically contains a group of files that contain different version of a set of records. So essentially there's a base file, and then there's a set of log files. The log files encode updates or deletes to the base file. Think of them as a change log specifically for that particular base file, right? And the base files can be Parquet, ORC, our own SS table based file format, open file formats. And log file again contains some, metadata, and the container is still an open format like Parquet or Avro. Right. So we also support Avro in the log files so that you can quickly write row-based data and then, amortize the cost of writing columnar Parquet files, which can be like 10x more expensive than writing row-based data. Right. So it's generally how the storage layout works. So there is, in summary, tables are partitioned, split into partitions. Optionally, partitions have file groups. File groups have a bunch of, kind of what we call file slices, which represents a base file set of log files. We'll talk about what slices are a little bit later. And each of these records also are individually versioned. Every record, for example, is stamped with the commit that wrote the record. Right. This helps us implement change, capture, and other things like that later on. The metadata now is stored, in a special folder under the base part of the table. It contains transaction logs, what we call a timeline, which is essentially an event log. It records every change that you make to table state within that. And then there is a file that contains table configs. There is a metadata folder, which contains all the table metadata and the indexes, and some temp folder to deal with some auxiliary things like, write tracking and stuff like that.
Actually,
So
this is a stupid question. Like, so,
yeah.
I've always pronounced it as Hudi, but you've been saying Hudi, and then now I look at your layout here, and you have Hudi, Hoodie.
Yeah.
What is the etymology of this? Like, why did you guys have to change when you made it Apache?
Yeah, so somebody complained about the name, so we had to change it because of the ticket's still in the GitHub, I think.
Okay.
But we are already live. Lots of people already used it, so it's kind of like it stuck around as one of these quirks in the project and a fun story to tell people.
Got it. Okay.
Renaming them, that would take we had to take a downtime. So yeah.
Yeah, no, of
So
course
when
you
we
did.
donated it to Apache, somebody complained.
Okay, awesome. Thank you.
Okay. All right. Now, so I touched upon this a little bit, the base files and the log files, right? So the logs are basically a differential data structure added to reduce write costs. So if you're updating stuff, the simplest way to deal with it is what we call a copy and write table. Writes come in, you just read the Parquet file, sorry, and then change only the records that have changed and then write a new Parquet file. But this can be expensive, as you can imagine, right? Because columnar data is a lot more expensive. So we also support something called merge and read, where you kind of queue up, append all these changes to log files, associate them with a base file, and then you accumulate enough changes and a periodic background compaction then takes the log files, applies the changes to the base file, and amortizes the cost of writing these expensive columnar Parquet files. So this is something that we call merge and read. These are two table types that we have in Hudi, and there are trade-offs here. The copy on write has higher write cost, and MOR could be lower. The data latency could be slower because writing Parquet is actually more expensive. And if you write row-based arrow changes into your MOR tables, then the data latency could be like pretty fast on an MOR table. And query speed can be really fast on the copy and write tables. It's almost like scanning a Parquet table, right? Pure columnar query performance. And the query performance on the MOR table can be slower before compaction. Once the compaction runs, makes new Parquet files, it's just like querying any other Parquet file, right? So these are a couple of levers that people have to trade off all these different changes. And next we come to the timeline. The timeline is pretty central to Hudi's operations. It's designed as a transactional, like an event log, like I mentioned. So each action, essentially any action is any change by a writer or a maintenance operation to the table state. And each of these actions have a state, which can be either an action can be requested, in flight, or completed. And they have a a requested time and a completion time along with it. So if you look at the image on the right, it basically talks about how you can think of actions as like intervals along time, where something starts, it's in flight, it can fail multiple times while it's in flight, and then it finally commits. And actions changes don't take effect unless it's completed, right? And each state, whenever it changes state, it writes a new file under the metadata folder. And the requested state often has like plans associated with it. For example, if you're planning a compaction or a clustering, we serialize the plan for that operation within that as well, right? The timeline itself is implemented as an LSM tree, which is a really proven data structure for storing this sort of like time-based logs and event data, right? And the history goes into this LSM tree structure, while the what we call active actions, which is either stuff that's in flight, requested in flight, that are not completed recently, all of them stay in an active timeline. And a background process will automatically move stuff from the active timeline to the history, right? So this is designed so that we can support large amounts of history and also frequent writes to the table state change. Again, given all of this is on cloud storage, we need to do efficient management of this metadata as well to have very scalable tables.
All right, so there's two questions in the chat. One is, what's more popularly deployed, copy and write or merge and read?
I would say based on the GitHub issue searches, it's about 50-50. Copy and write is used by, I would say, like typical analytical tables, downstream things. A lot of people use MOR for quickly landing data, streaming ingest from CDC, streaming pipelines, anything that requires some level of concurrent writing or faster, writes. I think MOR is a good key choice.
And then another question is, are actions basically DDL changes and then internal things like compaction?
Yes, the actions high level. Actions are internal tables, so it's like compaction, clustering, save point, restore, anything that can change the state of the table, and also the writers, right, which includes all these different relations.
Again, guys, if you want to ask a question, just unmute yourself. Joseph, you want to unmute yourself and ask it? If you're able to.
Yeah, absolutely. Absolutely. I was just wondering at Uber scale, how slow was the compaction for Hudi? Maybe in terms of numbers. Yeah.
So for Uber, it's hard for me to recall like a compaction number, but the original architecture that we had when we pre-Hudi, we ingested every 8 hours. With Hudi, we were able to ingest every 20 minutes. For compaction itself, we didn't have a good baseline to say it was this slow, right? Because previously we didn't have compaction. Does that make sense?
Yeah, it does. Thank you.
Hey, Vinoth, one question. So the timeline is a log. I'm just curious, why does it require a LSM tree to build to have that log? And
Yeah.
so,
Great question. So if you look at this architecture, like we discussed, we don't want to store any of the metadata, not just the data, just the metadata on anything except cloud storage, right? That way, the whole table can be self-contained on the cloud storage. So now this answer goes back to the limitation of cloud storage itself. It does not like a lot of small files, right? So if we, for example, keep writing table history as like let's say one file or object per action, it will become like quickly unreadable. If you try to go access it, just listing it or just even accessing that would take like lots and lots of minutes. So what we do here is we take the historical actions, and we kind of write them out as an LSM tree based on Parquet, because we can then kind of flexibly query it based on just the time, or we want the actual metadata for an audit trail. So it gives us a lot of functionality and efficiency to query the history.
so the LSM tree is for searching, not for for efficient searching of the log.
Efficient searching of the timeline history, yes.
Okay. Okay. Thanks.
All right, cool, great questions. All right, so next we come to metadata, right? A good amount of, for example, the database functionality, that the goodness comes from access methods, which are indexes, and also built-in metadata tracking by the database. The database tracks what files are valid on disk and like does all of that bookkeeping for you, right? So we need a similar mechanism here. So Hudi stores all of its table metadata in an internal metadata table. It's another MOR table that is stored, alongside every Hudi table, and it broadly contains two kinds of metadata. One is table format metadata, which is stuff that you need to identify table snapshots, like what files belong to what snapshots, used by the query engines typically to plan the queries. And then we also store indexes. Indexes are used by the Hudi storage engine itself to speed up queries and writes, as we will see in future slides. And these are kept up to date by any writers or tables. Anything that changes the state of the table will make sure this table is always in sync with the data table. All right. So putting all this together.
So what is the data structure you're using for the secondary indexes?
We are using, so it's another Hudi table, so it has a base file and a log file. The base file format, however, is a SS table based file format where we use to explicitly index the column stats and things like that.
Got it. Okay, thanks.
How do you make the metadata atomically updated along with the write? Like it's different file. Like someone will read an outdated or newer version than what was already written.
Yeah. So just to repeat the question, how do you keep the metadata on the data table up to date? So at a very high level, we built a parent-child relationship between the metadata table's timeline and the data table's timeline. So nothing in the metadata table is committed until it's committed in the data table, right? So that gives us like a good way to write to the data table, metadata table, as well as keep everything consistent and atomic. All right. So just to wrap this up, at a very high level, here's how the read and write paths work. When you write, you add records, to a file group or a file slice, the latest file slice. Either you create a new file slice by adding a new Parquet file if you're copy and write, or you write a new log file into the latest file slice if you're using merge and read. And then you commit to the timeline and keep the metadata table up to date, right? On the reading side, the query engines obtain, read the metadata from the timeline and the metadata table, figure out what are the right, snapshots on the thing, use the column statistics or things like that to, prune and plan the query. Then you just go read the actual file slices that you need to read to answer your question. So if you're, for example, a time travel query, you need to read like a previous file slice. If you are the snapshot query, which, you want the latest snapshot, then you read the latest file slice, right? So this is high level how reads and writes work. Okay, now that we understand the layout, right, time to solve some hard problems. And a lot of these questions are great because some of them touch on this kind of storage engine functionality that we will cover in the next slides. Okay, first and foremost, the layout here is very challenging, right? For any database, as you can see, you can do a different trade-off on the write and read, and you can have a table format. That's generally what I think can be done, or a storage format for that matter. So this is particularly challenging because it kind of touches both, traditional OLTP and OLAP. We want the system to be optimized for analytical scans, which means the data can be sorted. It can be in many different ways. The organization has to be purely be driven by the queries, right? While at the same time, we need efficient record level operations like OLTP like. I say like because it's not a OLTP system, but it should be fast enough to absorb any updates to an upstream OLTP system, right? If I need to keep up with the 2 million records per second updates to an upstream Cassandra table and replicate this scalably into the lake, right? So that's a goal. So a good reference that we use for this is the Rum conjecture, which I believe was covered on this course actually many years ago. If I'm not, maybe I'm wrong.
So this seminar is not part of the course; it's just general database stuff. But like we cover this in the advanced class, yes.
Yes. Okay. Cool. So it basically states that when you design an access method, and like for read, update, and modify these three trade-offs, if you optimize for two, it's not possible to do that without adding a cost to the third, right? So if you can see some of the choices here, right? So if you look at the triangle, think something like file snapshots. I'm sorry, apologize if that's not very legible. Something like file snapshots that represents things like Iceberg or Delta Lake. They're tracking files and like how files make up snapshots, right? Even with their recent MOR variants, they make it like more update optimized, right? And newer formats that are LSM tree based optimize purely for write speed, because an LSM tree is great for like append writes or like random updates even, right? But in my opinion, that's not the right trade-off to make here on the lake because it's very read-heavy system, right? Lots of analytical queries scanning a lot of data, right? So what we ended up doing was we decided to take additional cost on the storage piece, right? There's no memory component here; it's all stateless, but we decide to use more storage space to build indexes, right? To make sure that the writes now can have key-based indexes. So if you want to update something, you look up the index takes storage space, but you are able to quickly go update the file group that actually contains the record. And on the read side, this completely now decouples. However, we we can sort the table whichever way, right? Unlike an LSM tree, for example, where you need to kind of sort it by the record key, right? For it to kind of at least work efficiently. So you can sort it whichever way. So it's also like, read optimized, right? And then there are also benefits for the file group, right? This grouping of records helps us cut down read amplification for the merge because as in the picture, if without this kind of grouping, you end up merging all the, for example, the Iceberg v2 delete files, you end up merging all of them with every base file. Here you only merge the changes that are relevant to the base file with every scan. So it kind of bounds it, keeps the compaction tasks bounded in size. And then it also, the very important thing here is it preserves the data insert order. Which is very important in lakes, right? A lot of data arrives based on time, and then actually preserving that kind of insert order by default makes a ton of sense because, for example, you will build a dashboard based on time and you want it to work pretty well, and the locality is kind of important for these queries, right? Second problem is the data lake tables can be like really big, right? We at least have some 10 documented exabyte scale deployments for Hudi, and scaling this table metadata is a core challenge for us because of that. And the reason is the following, right? Like listing millions of files is slow and expensive. Rename on a cloud storage is a non-atomic copy, so you can't do things like rename. And you need to have the readers efficiently skip column starts during query execution. This is compounded by the fact that you can have wide columns. You can have large tables, wide columns, and lots of table versions as well. So if you compound all that, you quickly end up with a state where your metadata can be like really big. This is a great paper where it talks about similar challenges for BigQuery, right? And ultimately what we realized was we need to deploy a different kind of row-based file format, typically used in, like databases, online database, like NoSQL stores, to index this metadata a little bit better, right? So in short, what we do for this is we store the core table metadata, which is files and column statistics, indexed by storage partition for the files. And the column statistics, we kind of organize it so that you have columns, right? There are kind of clustered by columns. So if, let's say, you have a wide table and your query only involves 10 columns, then you only look up those 10 columns or 10 files, things like that, instead of reading like a single flat file with entire column stats for all the columns. So this is augmented with a smart metadata caching inside the storage engine. We employ memory, RocksDB, Sybil map, like bunch of different cache backends within, like, for example, like a Spark cluster along with Hudi to or any of these engines. Like it can all help to improve the metadata access. Time. So we talked about a timeline. So time is kind of important. So time is generated at the start and completion of every action here, like we discussed before. And time, the way time is used is used to order operations on the timeline. So writer, for example, a writer with an earliest completion time, earlier completion time, I should say, preceded a writer with a greater completion time, right? And a compaction, for example, with a requested time, which is kind of higher than a completion time of a write, kind of followed that, right? So these things are important for us to make sure we schedule the compaction to cover the right set of files, right? So we don't miss any log files, for example, during compaction. So the approach that we take here is kind of adapted based on Spanish true time. Of course, we are not in the business of OLTP databases, which makes this problem like lot easier. So essentially this chart, if you look at it, it maps real time versus true time, right? The basic problem here is there can be clock skew and difference in local clocks across different processes. But again, since we are not OLTP, the default implementation, we can wait long enough for a reasonable amount of time to iron out these issues. And we use a distributed lock to kind of generate time, wait, and then let the skew pass. And that helps us generate monotonically increasing times. Obviously, it can also be implemented differently with a global time generation service and whatnot. But yeah, this practically works for many large deployments. Now things get interesting. We want two writers to update the table safely, right? So specifically, we want something like something that works for data lake workloads, though. So if you just want to characterize the data lake or the Lakehouse transactions, they are nothing like old DB transactions, right? So they are, the real time writes in Lakehouse is like a minute or a few seconds, right? Which is all like, for example, when I was at Oracle, like something ran for a few minutes, that was a long running transaction. So all you have is like basically batched long running transactions, right? So we need and even if, say, we designed a system to support single record updates, low latency single record updates, again, cloud storage cannot support this. It'll have a lot of small files and objects and kill the query performance anyway. So I think what we need to optimize for is this architecture in Lakehouse, where we have high throughput batch transactions, right? But the key requirements here is as we need to be able to constantly maintain the tables using table services. Same principle, same motivation. If you do not compact and keep or remove like expired data using cleaning, then your table performance can generally degrade, right? So you need to be like maintaining the table constantly. And the key thing in this architecture is we don't have any long running storage service, right? So on data lake scale, record scale is generally 10 to 100x more than a warehouse or like other systems. So we cannot do things like pessimistic row level locks that can probably give you higher level of concurrency. Those techniques are not feasible here. So we solved it in this use case using a optimistic concurrency control, which is coarse grained at the file level, right? So this is what Hudi implements. And the basic way it works is there's a distributed lock. So writers write, they stage the data basically, and then take a lock and then validate the state before committing. And they do conflict detection on overlapping files and do like, version checks and things like that. So you essentially, one of them aborts if they detect a conflict, right? That's generally how it works. But OCC barely works when there is even a small amount of conflicts, right? And if you where it becomes very problematic is given the nature of these jobs that are running on thousands of cores for hours, right? And computing something and finally, output something. If they keep failing, or if one writer starves or keeps failing, it can cause like massive wastage and kind of heartburn at scale, because you ran a, like, for example, like a big batch Spark job and then it finally didn't commit, right? So that's not a good outcome. So we added a yearly conflict detection mechanism to go alongside, where as the write happens, it keeps checking whether it would, based on like out of band auxiliary like marker files and other mechanisms, on whether it's going to eventually abort. If it's going to eventually abort, it basically the driver kills itself, and then at least like relinquishes the cluster time. It's an optimization. It's obviously not guaranteed to catch cache everything, right? Avoid the whole thing. So this is actually our next problem to solve, because this issue of I want to write and keep maintaining, right, is a very common thing, right? For CDC pipelines, for example, you need to like constantly, keep listen to a CDC stream and then keep applying the changes. As you apply, you are generating kind of new files. You need to either do some compaction or some table maintenance to keep the table in shape, right? And if your table maintenance keeps kind of failing and starving from the writer, you can experience very bad query performance, right? So this is what is basically depicted here, where if you have a shorter writer, it can actually starve the table maintenance always, right? So you'll try to it'll run for some time, it'll try to commit, it'll fail. By the time you retry it again, but there's probably like you're actively writing to the table, it fails again. So we have special handling for this particular use case. We do something, I think, novel here. And what we do is we actually distinguish between scheduling of the compaction and actually executing the actual compaction, right? And so you have a merchant read table. The writer writes a bunch of log files to an existing base files, like 4 file groups there. What we do is we schedule a compaction, right? We take a distributed log, we pass the world for the duration of actually planning out the compaction. We serialize the compaction plan to the requested state in the timeline. This is where the timeline comes in like very handy, because it helps us notify all other writers that, hey, a compaction like this is going to happen, and all the writers and readers adjust their view of the table based on that. So the compaction, we assume that the compaction will eventually succeed, right? It can fail many times and it can eventually succeed. But until then, the writers can add more logs and everything to the newer file slice, and life goes on, right? So if this is a very, very key thing that Hudi does, which makes it a good fit for CDC streaming workloads. If you're ever curious that you know, in your chat GPT or anything, if you punch in why is Hudi different or anything, if it tells you Hudi is good for CDC and streaming workloads, this is why. But the approach that we take here is pretty general purpose, right? This also helps for example, two large batch jobs, kind of, you know, writing to the same thing, like a compactor removing deletes, applying deletes while you're adding new data to the table. So yeah, this is like super handy. It solves a really big class of a very common concurrency problem for us. The other thing we've emphasized many, many times is read and query performance is king on the lake, right? We have lots of reads, but it's not that easy to achieve. Cloud storage has very high latency, low IOPS. By that, if you think of this as a disk, by that, what I really mean is if you like do too many calls, it'll throttle you, right? Essentially, cloud storage is simply a HTTP service that you talk to using, I don't know why, but still here HTTP 1.1, right? And then you need to avoid small files. So if you have a lot of small files, the amount of get calls that you make will go through the roof. So a lot of bad things will happen. So file sizing, layout management is super critical to control our cost on the lake. Hudi basically does a few things here. The storage engine functionality, write operations ensure target file sizes. So it has a bin packing algorithm where it tries to figure out, okay, for this write, it profiles the workload and figures out how to pack the data so that it can meet that target file size. And there is background clustering and reordering that you can do to resort the table. You can use z ordering or linear sorting, Hilbert curves, things like that. And we maintain file groups as the unit for concurrency control and compaction for throughout all these different operations. All right. So far we saw how we scale metadata, like how we basically covered a lot of the table abstractions, right? Remember our goals. At the start of the talk, we said we want the lake to behave more like a database. So if we are to achieve that, we need to fundamentally make the record level operations for reads and write way more performant, because that's kind of like what makes the database not even performance, it's easier to deal with. You can write stuff, work with records and not worry too much about files, right? And there are two classes of problems to be solved here. For writes, if you have updates and deletes, let's say to less than 1% of records in a petabytes of data, how do you do that efficiently, right? So I've summarized some very common needs we've seen over the years. These are real OSS users with, kind of real workload shapes that we've seen. Amazon package delivery status, financial transactions changing and how you update a few transactions changing in a large table, delete a few user events amongst hundreds of millions of users, right? So for all these merge operations or delete operations, if you scan the entire table, it can be prohibitively expensive. On the queries, there are needle in a haystack type queries. You want to, like at Uber, you wanted to look up one Uber trip, right? What happened on that one Uber trip? Or for something like a retailer would want to look at status of all orders for a given customer, right? Something like that. So these require a separate system, right? So Hudi's approach here, we have like about half a dozen write-aside indexes. So we've implemented these indexes based on actual write patterns that we've seen. So we broadly characterize the writes into three patterns. One is random updates to dimension tables, like any record can get updated at any point. So the write amplification here is like super high. Even a single record changing in every file will like kind of you have to rewrite the table ultimately at some point, right? So here you can simply do joins against the whole table if the dimension table is small enough. We also support a record index, which is essentially a hash bucketed index with backed by the same SS table file format that I mentioned. And it consists like a bucket index and a consistent hash index. You can use hashing. Obviously, this messes with the layout of the table, but there are options for the writers to pick here. The second is we've seen skewed updates to large fact tables, right? Where a few recently updated partitions, your shopping cart history, things like that, where there's a large amount, the table is actually much bigger, but there's a pattern. There's like some sort of like a Zipfian pattern to how the updates trickle across time. So here, I think record level index is again helpful. We also seen a lot of users use Bloom filter indexes because they quickly weed out all these, for example, the yellow partitions, all the white ones will quickly weed out all of them. So you end up like processing way less data than than scanning the whole table, for example, right? And deletes against large event tables are actually very challenging, right? So the issue here is the data scale is so high that even if you have like a record level index across the table, it's going to be it's a lot of index, right? Even at that point. So we built something called, we also have partition level indexes. So the most of these event tables, if you look at them, a lot of them kind of move. There's like a window of time, right? So the data is valid for some time and then it goes into rest. So the partitional index actually follows that pattern. So you maintain the indexes at the partition level or the folder level, basically, not at the table level. That way you keep up with the write volume. You're not your index maintenance problems don't become O of table size. They become O of the amount of data that is written, which helps you kind of scale the writes linearly over time in terms of like data volume, not table volume. On the reader side, we also provide, this is something that we implemented for Spark, when probably rolling out other engines over time. You can create like secondary indexes on columns in the table. You can create indexes on expressions of columns as well. And then we build these indexes, and you can see, it's kind of obvious that with an index, something like a TPC, any query that can use an index would see, much greater data skipping and much lower latency. So yeah, so we support essentially database like indexes on both reader and writer. That's the takeaway. All right. The lake has columnar reads, but what about writes? Right. So this is actually one of the least optimized areas even in data warehouses. But today we all want data faster. Data needs to be integrated continuously over time, lower processing time. So we need we need to embrace updates, right? The whole Lakehouse, the category and the popularity of the whole category is also based on, for example, a need for updating data, which was previously immutable, right? So merge operations are very common in ETL pipelines to accomplish things like that, right? And oftentimes they actually end up only changing a few column values inside a record, right? But most of the current implementations, if you look at it, they work in the following way. You have a merge into statement, and then once you figure out the new values to write, you are in some way like reading all columns for all the updated or touched records, and then you end up writing new files with deletion vectors for all the marking in the old files that these values are deleted, and then like in this case file 8, 9, 10 contain full images of all the updated rows, right? While file 147 also contain the full images of the updated rows, which are now deleted, right? So this can be like pretty cumbersome when you have, again, white tables or even just tables where just only a few columns are changing, right? Very large table. Otherwise, you'll have to end up rewriting a lot of data, right, over time. So Hudi also does columnar writes, meaning like we just encode the change columns, and given the file group abstraction that we already have, we do it right next to the base file. We can exploit the columnar nature of the base file, and also these processing engines, which can kind of read them as arrow vectors in a columnar fashion and merge them. So we do that and implement a very efficient merge actually. So you can see this is kind of like a win-win across the board, because the log file points to, hey, here are the columns that are being changed, and we know the rows that have been changed with the vector already. So we write an update vector, not just a delete vector. This way, when we do a scan for the file slice, we're able to actually figure out what we need, exactly what column values to suppress and whatnot across different columns, right? And it actually improves update latency because we are writing fewer bytes. We are not writing all columns, we're only writing the change columns. The total amount of data stored goes down because we are only again storing the change columns. And the query latency also goes down because we are fundamentally reading fewer bytes, right? So it's just like a win-win across the board. And this actually is a foundation for us to support white tables and unstructured data that I'll cover at the end. Finally, the last frontier for us is the data processing world has significantly changed, right? In the last decade, I had front row seats into the rise of Kafka and stream processing at LinkedIn, and then I even tuned our JVM clusters for Kafka at LinkedIn and have done enough Kafka for one lifetime, I would say. So stream processing obviously offers different way of processing data, right? So it kind of like deals with data as a stream, and there are new problems that come with it. You need to handle data can be out of order from the sources, and you need processing not just based on arrival time, but based on event time or like some kind of business field within the data. And a lot of cases there can be dedupes, copies of streams, all these kinds of issues. You need a deterministic deduping mechanism and all of that, right? If you want low latency and high, so there's like a lot of desire to get these on the lake, right? Without having to copy all your data into Kafka. This is the great divide right now, right? The world split into streaming and batch systems, right? And streaming is you put it in log is your storage, Kafka and the Kafka-like storage systems. Or on the other side, you have batch systems, which are essentially lakes and warehouses, right? So what we wanted to do from the get-go, going back to that incremental use case that I talked about, right? We wanted to actually cut down we wanted the pipelines to run in a more natural way, right? All of that processing is nothing but, so we already made a lot of progress towards that, right? So for low latency and high efficiency, for this kind of workload, this kind of processing, blocking should be as little as possible. So Hudi does three things here, specifically to bring more incremental or streaming style processing on the lake. So of course, we already made the writes faster using indexes and stuff, which helps. It's like how a stream processing state store behaves for fast, kind of mutations and merges. So that's a start already, right? But we go beyond that. What we do is we implement first-class support for event time. So the base and the log files that I talked about before, we can configure an event time field for the table, and then we can actually merge these records based on the event time and not based on the commit time or the actual arrival time or the system time, right? So this is very, very helpful for things like out of order data. Maybe they have a table that is being fed by two database change logs, and there's duplication. You see older state of the table again, like all those things, right? It's super, super helpful for avoiding things like that. The example here shows, how an order system and a payment system are emitting events for the same order. And obviously, these microservices can be up or down, have bugs, anything really, and then emit events out of order, right? But you still want to consistently, deterministically merge them based on an event time and not the system time, right? Second, like a database, Hudi provides CDC streams. They are encoded. So CDC blocks and logs are encoded right next to the base file in the log files themselves. Right, CDC query is probably more self-explanatory. It provides kind of before-after record images along with the operations that cause the changes for insert updates and deletes within that time window. We also provide something called an incremental query, which only provides the latest state of the record, right? It does not provide all changes. Let's say you updated the record 10 times between T1 and T2, it'll still give you one value, right? The latest committed value within that time window. This again is very useful because as we as you saw before, as a system, we are constantly compacting the thing, right? So let's say we are writing to the table every 10 minutes, committing every 10 minutes, compacting every 10 minutes, but you're querying every hour. Now you want to actually amortize all the work that the compactor has already done for you. And if you just want the latest state of the table to sync, you can use the incremental query. A few other systems also support this for the same kind of efficiency needs. So previously we talked about limitations of OCC, right, and how non-blocking is implemented. But we left that at the two writers are still blocking each other, and that's not good if you want to have some kind of streaming semantics, right? Stream processing, if you look at it, typically two producers just serialize these writes into a log and avoid the concurrency and get some kind of deterministic ordering. That is how they actually end up solving it. Hudi adapts this for the lake. We move the log to the file group, basically, right? And then we implement non-blocking concurrency control where the writers don't block on each other, even when updating the same record of the columns. The records they just write, and then the records are merged deterministically, either based on commit time or event time based on the semantics that you want. And the compaction also can be performed async and non-blocking like before outside. So this is like brand new functionality that we introduced like earlier this year. As of now, Hudi is the only system that can support, for example, two Flink streaming jobs writing to the same table without one killing, like they're constantly killing each other's writes otherwise. All right, quickly wrapping up. There's definitely a lot going on in this slide, but I'll keep it very quick. This is generally what a Hudi deployment looks like. People use a lot of tools that we already have to ingest data sources from databases, microservices, event streams, what have you, using Spark or Flink. They produce a series of tables. And then Hudi has a lot of support for these different catalogs. It basically is designed as an external storage system that can sync your tables to multiple catalogs, because as we know, catalogs are deeply coupled with different query engines, right? So we want to be able to support querying from all different open source and commercial query engines. And all popular engines and clouds warehouses, except one, can directly query Hudi tables. And for that one, we also support a Xtable sync where we can expose Hudi tables as Iceberg or Delta Lake tables that can be read by engines that don't natively support Hudi reads. So a popular deployment for people is they use something like Hudi to get all of this is open source, whatever I talked about right now. So they can actually save a ton of money on the infrastructure by building an open data lakehouse on top of Hudi, keeps it kind of like loosely coupled from any one engine, and then you can expose your data through different engines. Right, that's generally what we see. I'm pretty sure you're all curious about this, given the last speaker and the series itself. So I thought like I'll leave you all with a mental model of how to think about this. The space can be quite confusing because there's lots of interest in the space, and also this model kind of collapses and split layers very differently, right? So if you actually zoom back and think about it, there is a clear differentiation between the storage engine functionality, which is software. Right, we write open source software to implement performant updates, delete stream writers, like all of the stuff that we just discussed, from the table format, which is a specification for, okay, what a standard table representation should look like on top of cloud storage, right? So if you look at stuff like Iceberg, it focuses a lot more on like, it's designed more from the format and up, right? It's essentially like it's the lowest common denominator of what different engines support, and it's evolved by adapting newer features from things like Hudi, other formats, as we discussed in the last talk. Hudi is designed first and foremost as a storage engine with a format that is designed for the storage engine, right? So that is kind of like how Hudi's design evolves. And Delta is kind of similar to Hudi I think more in that regard, a lot more with some technical differences, right? So we've been also doing a lot of work in the Apache Xtable project to bring these together. The great thing about this is, unlike commercial warehouses with their own file formats and things, since the base file format here are mostly open file formats and shared, it's actually pretty easy to make the cross table format reading at least work like really well. Right, and with that, I think there's a final note on ton of cool innovation happening in the project. We with the columnar writing and other things, we already sown the seeds for white tables on unstructured data. So we are there's a lot of focus on bringing unstructured data into the Lakehouse as well. If you Google lake versus warehouse, you'd probably say something like lake is good at unstructured, warehouse is good at structured, but the Lakehouse completely is about structured data, right? So we've solved a lot of these hard problems for that, and I think a lot of them are applicable for unstructured data as well. So we are also working on pluggable table formats. A lot of the storage engine functionality that we built can actually work on other table formats like Iceberg or LSM, or introduce like LSM data layouts if people want LSM. So we are working on making that layer more pluggable. Deeper secondary indexes. There is we built 2. There's probably 10 more that we can build. Right, and some cost-based selection among indexes. Right now, it's not a problem because we have 2, but if you have 10, then we need to solve this problem. We're also thinking about caching. That's a core part of what we don't have. And from the picture that I showed you before, this thing is somehow like caching's been tied to the engine very tightly. So we're trying to kind of think through how to decouple that in a way that it can work across multiple engines. Non-blocking concurrency control, not just for compaction, but for clustering as well. And the other open problem is the index construction. How do we make it for Flink streaming rights? Right now, Flink does support, for example, record level index and things like that. There's an inherent hard problem there where the Flink model is very, Flink decides what a commit is right now. But we don't want to commit until the index and the data are in sync. So there's some hard problems to be solved on that front. Spark gives you a nice synchronization point on the driver because of the micro batch model, but Flink is pure streaming, right? So there's a lot of work to be done around that, right? If any of this is interesting, and if you want to can I engage with us, here is where you can go. There's a site for the docs. GitHub is where everything else is. There's a Slack community with maybe around 5,000 people there, LinkedIn page. This is where you find us. I hope this was useful, and thank you so much for having me here.
All right, so I applaud on behalf of everyone else. This is actually a fantastic talk. You covered all the important stuff. I appreciate it. We have time for one question. We're a little over time, so one question for Vinoth before we call it a day. If you have a question, unmute yourself. Otherwise, I will take the time. Okay, so when you talked about the true time piece, I think basically what you're saying is, since it's decentralized, all of the whatever different query engines that are talking through the Hudi API or the library then start modifying files in the Lakehouse or the lake storage. Each of these systems are basically coming with their own timestamp. Is that correct? But then it sounds like if it's a hosted service, you could then call out to a time service, like whatever the Amazon one is or Google's own thing, right?
Yes.
In practice, though, if you're not using a centralized time service, how challenging is it to get people to make sure the various systems in the same organization are at least running they're running NTP or something like that?
Yeah. Great question. So practically, we measured this before at LinkedIn because Walmart, which was a system that we worked before, used vector clocks and had timestamps as well. So the NTP in data centers are actually, 0.1 millisecond. It's less than 0.1 millisecond, the drift between them. And even right now, if you look at AWS, lots of these data cloud providers use synchronized clocks, like GPS clocks to atomic clocks to actually synchronize the time. So it's mostly in sync. On top of this, what we do is we are not a OLTP. We can afford to add a 500 millisecond wait or a few hundred millisecond wait, and it'll practically eliminates the problem altogether. But if you're really paranoid, you can create a file on S3 and use the file's creation time as the timestamp, and they will give you theoretically completely ordered timestamp.